So our speaker today is Bruce Albrecht. He received his doctorate from CSU and then was at Penn State for 18 years, and he's currently the professor at the Rosenstiel School of Marine and Atmospheric Sciences at the University of Miami. He's also a former department chair at the same. His research interests include atmospheric convection, boundary layer structure and clouds, turbulence and microphysics measurements from aircraft, and surface-based remote sensing of clouds. He's had key scientific contributions in the trade wind boundary layer, marine stratocumulus clouds, cloud aerosol drizzle interactions, and millimeter wavelength cloud radar observations. He's recently the recipient of the CSU Distinguished Alumnus Award, 2006, and as I said, past chair, department chair at Miami, former editor of the Monthly Weather Review, former secretary of the Atmospheric Sciences section of AGU, the current editor of the Journal of Atmospheric Sciences, and recently honored as a fellow of the AMS. So that, Bruce.
Thank you. Is this working? I guess so. Okay. Well, it's a pleasure to be out here to talk about CSET. And a number of the people here were in CSET, so what I'm going to talk about today is going to be a little bit repetitious for them, but hopefully for those of you who are not familiar with CSET, we'll give you a good idea of what happened and some of our initial results that we have. CSET's the Cloud System Evolution in the Trades. And I should point out that the PIs on this are actually myself and Pakita Zwaitema, Chris Bretherton, Rob Wood. I've got Hans down here. He's a graduate student, but he's did so much work that I had to put him up on the top list here. So I'll talk about that later when we come in. And Verenda Gate is there. So I think everything, but to make this work, there was a whole large team here, and many of the people from EOL were involved in this, and we had scientists, graduate students, postdocs, scientists, engineers, technicians, and pilots, of course. And so I hope by the end here, I'll not recognize everyone by name, but I certainly want to thank everyone for the contributions that they've given. So the purpose of this experiment was to study the evolution of the boundary layer along trajectories in the Pacific trade winds. And this is something that people have thought about for a long time. If we look at a typical satellite image here, we see the trades are moving down in this direction here, and we find these solid cloud layers giving way to the more broken clouds, the mesoscale convection that's in those areas. There's a blow-up showing here. So from a modeling perspective, that's important to get right because these clouds have such a large impact on the radiative features, or the radiative balance, that where they break up and how they break up and what happens after they break up is very important to trying to understand the cloud feedbacks within the climate system. So the idea here, though, is we're going to try to characterize the boundary layer conditions along trajectories and then try to simulate the transitions between these different convective regimes. So the scientific objective is this kind of, again, as I said, we're looking for the evolution. We're looking for cloud precipitation aerosol fields as they transition. We were going to examine the cloud microphysical properties, the boundary layer clouds, to determine how the internal and external processes work within these cloud systems. So those processes are important. In the end, we hope to provide some comprehensive studies to evaluate and improve process models, LES, GCM, StratoQ, for looking at the StratoQ transition. So I think this is reasonable objectives and a goal that I think we've made some progress towards, and I haven't done it yet. The design of the experiment was a Lagrangian approach. So the idea is that we sample clouds upstream near the stratocumulus regime, and then we make measurements in that area, and then we follow that down into Hawaii. This is where we were in our flights from California to Hawaii, and then we wait a couple of days, and we go back, and then we try to intersect the same air masses that we had sampled 2 days earlier. So that's the idea. Is we call it a Lagrangian approach. And the idea is that sort of simplifies things. We don't have to worry about the advection term when we're trying to look at budgets. And so that gives us a heads up on trying to deal with that. So the way, and I'll talk about this a little bit more, it's sort of the G5, its performance and some of the new remote sensing capabilities that really made this experiment possible. And here's just a brief list. I probably missed some of the things on here on the instrumentation, but I just want to point out a couple of things, and I'll talk about these later. But we have the Remote sensing was a HyperCloud Radar, HCR, that has gone through development over the last several years. And this was really the first project in which it was really fully operating and was an integral part of the experiment. There's a high spectral resolution LiDAR, which was another important component of this. There was a microwave radiometer. We had a temperature profiler. We had meteorology, turbulence sensors, the typical cloud physics, aerosol, and precipitation probes, including CN, aerosols, clouds, and precipitation. And there was this instrument, a holodeck, which Suzanne Raymond Shaw was involved in getting us into the program. And it's a holographic cloud imager, so that's a very interesting component there. Radiation sensors, chemistry, CO, ozone, and dropsondes. So here's, again, I just go talk a little bit more about this, the HyperCloud Radar, because this is really was a very important engineering accomplishment by putting this together in a form in this pod, which is specially designed for the airplane. And so the radar itself has an antenna in here which can be steered, so the beam can go up, it can go down, it can be scanned in other directions if you want. And at the same time, there's compensations that are made to account for the aircraft motions, and so that takes out some of the uncertainty that we have as we're flying along and the airplane is making motions. Here's just some examples of what the cloud radar picks up, and I'll be talking more about this particular case a little bit later, but here's the reflectivity, and this is the Doppler velocity. So this is I've got this in a form that down is negative. And so here's rain coming out here, for example. And I will be going over that more specifically later. Here's the HSRL. And this is an instrument that Ed Alranta has been involved with and helped put together. And it it was mounted in the cabin, and it takes up a fair bit of space, as you can see, but it points downward and it points upward. So when we are above the clouds, we would point down, below the clouds, we point up. And this is, again, some returns from the LiDAR as we're going along here. Now, this is sort of the setup for our field operations. And as I said before, it's sort of the capabilities of the G5 that makes this possible, because if we want to sample these clouds in this area that we're looking at here, we have to have an aircraft that has the range to do that. And this aircraft does have the range, but its best performance is actually at upper altitudes. So to really make some measurements in the low levels here, we had these low-level sampling strategies that we had here. We had to start out our flights at higher levels, usually at 20,000 feet, and we ended up at higher levels so that we could make it to Hawaii at a pace that was comfortable for the pilots, for they had enough gas and land and all those other important things. So this was the basic sampling strategy that we had. We'd fly out, we'd come down, and we'd make a profile down through here, we'd make a level below the cloud, we'd go up, make a level near the cloud base, and then we would do these porpoising type of flights at the top, then do a flight above the cloud where the instruments are looking down, and we repeat that as we went along. So we'd fly along, do a low-level segment, then repeat this segment as we're going along, and at which point we had to drop up. During these points here, we were doing the dropsondes. So at 20,000 feet, we would, that you can see on this particular flight where those dropsondes were made. So important part of this was the mission planning. And this is where I mentioned Hans before, because Hans would put together these trajectories, forward trajectories, so predicting where the air masses were going to be. So if these stars are the starting points, these were the end points down here that you can see. And so he would set up an array of these points, and then we would choose points such that, one, we could sample something interesting on the upward part, and two, when we get done, we can hopefully sample the same air masses again. So for example, the trajectory over here is going to be over here by Hawaii, so that's not going to do us any good. So this would go on every day, and here's the operations center at University of Washington, and they're busy doing that. And we had a telecon at Sacramento where the G5 was located, although when it was on a mission, it would be 2 days, it would be in Hawaii, or it would be a day in Hawaii and then it would come back. So that was a very important part of this. I also want to point out the field catalog was a very important tool for us to use in both the forecasting that we were doing here, or our planning of flights. It was also a very important tool during the operations. So this is just a screenshot of what the field catalog looks like. And the nice thing that you can do is you can overlay the satellite images with where the aircraft is. And you could do this in real time too, so that was very valuable. But for the planning purposes, we could do these simple overlays with the trajectories here and come up with a product that we could use. And while the aircraft is flying, both on the aircraft and on the ground, we could see these same views. Here's a camera off the right wing here that is looking forward in that case. Now, we had a total of 16 research flights, and we had 7 Lagrangian missions. The first mission we had was a short one. There was a failure with the, it wasn't the AC, it was the power of some sort. And so we had to go back, and we ended up back here. There was a last mission where we were doing some other things. But here's the tracks for all these different missions. So these can be paired up. For example, 2 and 3 was a pair. 4 and 5, 6 and 7, 8 and 9. So again, in total, we had 7 Lagrangian missions, and that amounts to about 20,000 kilometers of low-level sampling, 20,000 kilometers of high-level sampling, if you kind of make a rough estimate of what we did. So we covered a lot of territory during this time period. And what I've drawn here is sort of this is the subtropical high, or the anticyclone that you can see out over the Pacific. So this is the average for that period, and these are the average wind vectors associated with that. And the position of this high did vary, move north and south a little bit. The strength varied a little bit, but in general, it was a fairly well-behaved feature, not like some of the tropical systems that were down here lower that sometimes messed up our forecasts. So here, sort of an average look at what these trajectories would look like. So these red dots are sort of the average that we flew on the outbound flights, and the blue is the average that we flew on the flights back. And you can kind of see that these trajectories basically follow the streamlines pretty well, which is consistent with what and how we think things are working. If things are steady, and for an average, that works out pretty well. And you can see that the sea surface temperature in these cases, we're going from here where it's 18, 17, even colder up part of the north, and down to these points in this area here where we're up to 27, 26 Celsius as we're going down there. So we had a large range of temperature variations along these trajectories, and we can see that these trajectories here were a little bit shorter than the other ones. So I think we did a pretty good job on this. Verenda has actually put together, for each of the pairs, has put together the flights here. And we have these boxes here that indicate where the sampling was done in the low levels on the outbound flight, and this is on the outbound, this on the inbound flight here. And so this will allow us to look at the conditions here and compare that with these boxes, the conditions here, compare that with these boxes and with these boxes. So because we're moving horizontally, we're sampling horizontally, you can't really envision those as a single point of observations. We have to think about this as being some kind of an average when we're making these observations. And so one of the things that you can see from this, Verenda's kindly put on the surface pressure here. You can see the surface, the anticyclone was a little bit weaker here during this first flight, fairly strong, this RF6 and 7. And I'm going to talk more about that case in particular. And so in general, though, the patterns were fairly similar, although sometimes in this case, for example, you can see that this pattern is much different than we had in some of the other later cases where we were flying like this. So overall, I think we were very lucky in getting what we had here. So I was going to show the RF6 and 7, and Paquita and student Mampi have been working on this case in some detail. So at some point they'll have to share some of the work that they've been doing. But Here's a movie that, this is a movie that Hans has made. And this shows the boxes as we're going along here. And then time's going along. This is a GOES imagery that you can see here. So you see how much the boxes have advected here. Here's the sampling boxes that we had done before. And then pretty soon you're going to see the aircraft coming back from Hawaii here at some point. And so we would plan our flight back. Here it goes. Okay. So we plan our flight back based on where we predicted those air masses to be. And Hans would also update those forecasts. So it wasn't a 2-day forecast that was producing where we were going to go. So these were updated. So even when we're in Hawaii, we get an update sometimes on the positions of where those boxes were going to be. So I'll let Hans talk about how accurate that might be. But I think in general, we did a pretty good job of getting that. So you can see sometimes this pattern here is a little bit jagged here. And you'll see some more of that in some of the others I'm going to show here. So here's the final pattern. So here you can see the initial points that were used. Here's the final points that were used, and then here's the three trajectories that go along for this particular case. And you can see in the video there how those features were changing with time. So let's just look at this one again here. And this is the RF6 and 7. So you can see here's the boxes. There was this little dog leg that gets in there, and we saw that a couple of times in our different flights, and so it made for an interesting flight pattern when we're coming out here sometimes. Another thing that I wanted to note here is that sometimes you see that these boxes kind of follow along the mean wind streamlines. And so if the system is steady, you can also think about, even though we're thinking about transition over 2 days, there's also a transition that occurs as we fly along these paths. So there is some information there about what is going on along these, particularly if you find some where they're following the streamlines pretty nicely, that you could actually look at that and see how things vary. So this is the flight that we're going to look at. So here, I'm just showing some of the satellite imagery here for these different times. Now, the way I've arranged these panels is this is sort of our first sampling area here on the outbound flight. This is near our last sampling area here on that outbound flight. And then 48 hours later, this is our sampling sort of as we start our leg back in. And then this is the point to the east. So you can think about it as going like this. Time goes this way, and this is west to east here. So you can see even from the satellite imagery, some of the differences in the clouds that we see here, and we'll see that in the radar that we saw too. Particularly as we got farther downstream in this direction here, much more broken cloud conditions, mesoscale cloud conditions. On the way back, again, we saw a lot of this mesoscale convection. I might call those open cells, if you want to think of it that way. And then this is the image as we're sort of our last part of the leg as we're approaching Sacramento again from there. So the transition from here to here is in time. Here to here is east to west, and so you can get a look at that. So just to see how the boundary layer appeared during those cases, that same format is here. And these were from the drop zones that were dropped closest to the point where we started the low-level measurements. And you can see here, as we start out, very similar to what we expect for the traditional well-mixed boundary layer with a sharpened version, fairly well-mixed conditions here. As we go farther west on that same day, there's some sense of maybe some decoupling. The boundary layer is a little bit deeper here, quite a bit deeper. It's up to about 1,700. It's about 500 meters when we started out, and but not some strong decoupling. On the return flight, in this same air mass that was sampled here, in this air mass here, we see that now there is some strong decoupling indicated here by the moisture profile. If you look at the theta E and theta S, you can also look and see this is sort of the classic kind of a sounding you would see with these broken cloud conditions. And then as we go farther east, even a sharper little transition layer here and a sharper layer indicating decoupled conditions in there. So we have clearly a nice, well-defined change in the boundary layer structure along here. Now here's the radar, some of the radar images these are our images. And again, this is at the beginning of the sequence, outbound, the end. And you can see here how we had relatively solid clouds during that beginning part, as you can see from the radar, and then breaking into these more mesoscale cellular structures here. And then on the return flight, again, we saw these mesoscale structures as we come back. And actually, when we got out to the most easterly part of that flight, we see that the clouds are really, we don't see as much in this, at least in this sequence, as much of the large mesoscale features that we saw farther to the west. And if you looked at the, I didn't show it exactly, but if you looked at the thermodynamic profiles, the inversion was not a lot higher here than it was here. It was higher, but not quite to the extent that you see in the east-west direction. Here's just something that Brendan had put together for the same thing. So this is the whole flight pattern. You can see how we're flying. And as we said, above the cloud, radar facing down, below the cloud facing up. And this had to be switched over. And the LiDAR itself had to be manually switched. The telescope had to be switched. The radar could be switched electronically by the operator on board. So there's our RF06 and RF07. So this is a picture that is quite good. We had a microwave radiometer on, so this is some observations that Paquita has put together showing the microwave radiometer observations. And you can see that there's some good structure shown in here with the microwave liquid water retrievals, liquid water path retrievals that she has from that. Verenda's also worked on looking at changes in drop size. This is for the aerosol drops, so I'm not going to talk too much about that today, but all those things are being put together for this particular case. Now, one of the things that we did have, we had a lot of variability in the aerosols. So this is an effective droplet radius. This is from Pat Minnis's product that he puts together. So this is for the experiment here. And this day here was the Canadian wildfires that were prevalent. That was on July 7th where that was happening. And which this effective radius, you see the blue or the smaller, red is larger droplets. So these are the cloud droplet size, effective diameters. And here you can almost see that smoke being wrapped around into this system in here. This is another case on July 17th, but again, you can see where some of these coastal areas are definitely affected by the aerosols that are going in there. So we've got a good chance on this case to look at some of that variability. And if you look at this case, this is the RF2 and 3, and you can see that the winds are basically coming out. This is bringing that smoke down into here. And if you look at the aerosols, well, here's the radar observations. This particular day is not necessarily good to look at the radar for various reasons. When it was looking down, it was attenuated out by an attenuation that was there to protect the radar. But that was later corrected. But you can. So this is only when we're looking up that we can see the clouds. You can see the differences. It picks up upper level clouds too. This is the. So the aerosol, this is the cloud, this is the aerosol, this is the USA. So here's above the cloud, but this is for research flight 2, so this is the output, and this is the equivalent box 48 hours later, and you can see above the cloud there's a very big difference there, and this of course is probably dominated by the smoke and other particles that were in there from the Canadian fires. We also see some differences this is below the cloud, there are also some differences even below the cloud between those two cases that were there. So that aerosol was probably affecting what was going on with the cloud. So this is another good case that we're going to be looking at for looking at the aerosol interactions. Now, one thing we did see, we saw significant aerosol cloud and precipitation features. And one of the things that, of course, caught my eye is the precipitation. And this is the same cloud that I'd shown you before. And so this is the reflectivity from here. This is the Doppler velocity. And just to give you an idea, this is about 15 kilometers here on the scale. So this is, I'm drawing this here so you can get some idea. This is the image of the clouds that we were sampling during that time period. I would point a little bit to a couple of things. One, there is a lot of structure in the precipitation that's falling out. Also, if you look at the Doppler velocities, you can see that near the cloud top it's near zero, but you still have reflectivity there, so it's still picking up some of those smaller drops. And then as we get closer down, we just have the precipitation. So some of this may be due to a couple of things. One, maybe the rain is growing as it's going down. The other thing is it's just sorted out by fall velocity, because in a 5-minute period, clouds that are moving at 5 meters, cloud droplets or rain droplets moving at 5 meters per second are going to be at the ground. So if you were to look, this wasn't a steady condition, if you were just to look at this image another 5 minutes later, it wouldn't look like this. You would have just something left up here that wasn't falling as quickly. So that's one of the things that we're going to be looking at. Now, it might be that this is just a steady system that just keeps generating and it's doing the other way. So that's the other part of that. So we can see that in some of the other cases here. Here's the next one this is from the camera here. And again, I thank Hans for this. So this is on this particular day. This was on the RF7 on the way back. So this is out of Hawaii here. So you can see these mesoscale patches here. So some of that reflectivity I was showing was just taken just before this patch here. So here we go, and now we're past some of that structure. And we got the other clouds there. So here's another, this is actually a radar for this at that particular level where I just showed you, where you saw that solid cloud. Here's another cloud, and notice that here, some of these fall velocities are greater than 6 meters per second that are coming out of there. So some big drops in there, undoubtedly. And as I said, that will definitely, it will rain out pretty quickly unless there's some kind of a source to keep it going. It's not gonna hang around like that. The other thing that's sort of interesting is you see this, as I said before, there's a lot of structure within that mesoscale system. So I'm not sure if those are downdrafts or what's going on there, but hopefully we have an opportunity to look at that. This is the LiDAR imagery from that same time period. And this is, of course, looking from the aircraft, we could see that there were quite a bit of clouds in that area. But some of these really had nothing below that the radar was able to pick up. So probably no big drops down below there. So here's the next part of this image. I like just watching these, so if you want to do this. So, I think we're going to put them all on tape so we can sit around and we can project them, you know. So now I was going to show you, well, look, as we're coming down in here, now we're descending down into the boundary layer. And I'm going to talk a little bit later about some of these gray clouds. You're going to see one right here. There you can see one of these gray clouds that's coming in. Now, there's going to be a rainbow coming up in here pretty soon. Double rainbow, actually. You saw that. And rain. And the camera's a great precipitation indicator, too, because we get splatters on the camera, and so we can see it going there. So our only regret is this wasn't real time when we were flying, because this would be a lot of fun, I think, you know, if we were flying that fast. But I'm not sure. But anyway, I guess, Paquita, you were on this flight, right? Yeah, is that what it looked like? So here you're going to see, again, now we're in an area where there's these little shallow clouds. We're going to send up here a little bit, and watch, you'll see some rain showers around here. There's a rain shower, splattering on the camera again at various points. And so I think we got some cloud samples on this one. You know, that looks pretty good. There we go. So now we're above again. Now there's some more of this stratiform in this area here. So when you look at this. Okay, so this is some imagery from that same time period of the radar. As we descended and looking up, you can see these clouds, tops are around almost 2 kilometers or so. But notice that there's some heavy precip falling out of these clouds. This is all downward motion in here. So even these small cumulus clouds can produce a double rainbow, if you like, as is from the camera from the front. And so the very efficient precipitators, just from our casual look at it. The other thing that we saw a lot of, and Rob Wood is working on this in some more detail, are these what we call gray clouds or an ultra clean layer. So if you look at this imagery here, This is 3 panels. So this is the LiDAR down below, this is the radar up above, and this is the LiDAR Doppler velocity on this screen here. So when you look through here, you can see these features, which actually they're optically thin enough that the radar penetrates through them, but or the LiDAR penetrates through them, but the radar picks them up, which means there has to be some pretty large droplets in there for that to happen. And so you can see several of these layers here as we're going along here. And the other thing to note is it's not showing quite so much, but we often find a very clean air associated with some of these gray clouds. Here's another case here where we can see, this is, if you look at this, there's like a mesoscale feature over before this, but extending out from here is a little shelf that comes out, and again, optically thin enough that the LiDAR can shoot through it, and yet we're still picking it up pretty nicely with the radar. Here's some more of those clouds in the background. So Rob has been working on this. Here's another one. Here's one of his slides that he's put together, and here just shows this is the kind of features we're looking at. Again, this is the same flight that I was just been showing you, and here's these clean layers, and you can see this. The LiDAR is a very good indicator of the clean layers. You can see a clean layer here, clean layer in these different parts. So these clouds are observed frequently, and the clean layer. This is from the HUSAS. This is the droplet aerosol concentrations per centimeter cubed, and this is the RF06. So this is the outgoing flight. This is the ingoing flight. And I just want to draw your attention to these blue areas here. So you can see the airplanes going up and down and everything, but these blue areas here, that's between 1 and 10 per cc of aerosols. So very, very clean environment in there. And if you look through many of the cases, this is observed quite frequently. Here's a slide that Rob has put together, and here's his optically thin, optically thick, in his clouds here. You can see the frequency for that. Frequency increase with height, as we see here, so cloudy clear samples. And so this is like 20 or 30% of the fraction of samples classified as ultra clean layers or in that area there. So he's going to be giving a little talk tomorrow. But later today. So if anyone wants to come up and join our meeting, feel free to come up and you can see some more on that. Here's just another one that Rob has put together where actually we had a place where the aircraft was doing an ascent and went cut right through one of these thin layers. And so you can look at the droplet concentrations here. So this is the red. So this goes over. The droplet concentrations are pretty small in that layer too, right? They're less than 10, is that right? Okay. And this is the drizzle droplet concentrations we have here, and a liquid water. So we have, in terms of physical processes that are going on, I think we've got a real a gold mine here for some of the stuff that we're going to be able to look at for these very interesting layers that we saw during CSET. The other thing I wanted to tell you about is that we also had another part of this of CSET that many of you may not even be aware of what's going on, but Shauna Donaher, who's an instructor at Emory University, she came out during the first part of the experiment, and she put together this cloud system evolution of trades educational module. So the idea here is that other instructors or other students on their own can actually do this. So this is designed for students, at least basic understanding of meteorology. And it could be used in different levels. It could be at just a very elementary level, or even advanced undergraduates or graduate students. You can also use the same module. And the idea was to try to make it feel like the students are experiencing what might happen in the field. So they had to go through these exercises, as you'll see, where she looks at basically describes the experiment, but also she gives students an opportunity to plan their own flights and see how they compare with what we planned, and then go through and do some analysis of the data if they like, and work that all through. So you can do it any level that you want. So if you go onto the CSET EOL page, you'll see a place where she has a a marker there where you can go in and you can look at this. And so I would encourage you, if you want, to go look at that. And so if you look here, then she's got the scientific background, about CSET, simulated flight, and data analysis. So then if you go into those tabs, you can find out more here. And here, for example, goals of the project, observation strategies, meet the team. You can go through all of this. She also did some nice videos of the field here. So, Jorn, I don't know if you know, you're on YouTube, but you've had four views, so don't get too excited. So I don't know if you remember when we taped that. So, but anyway, but she goes through and she has all the participants listed. She has a number of videos. Some of you in here participated in that. So if you want to, the students can go through in there and hear scientists talking about their work and try to get them excited about what was going on during CSET. She also has a video that Hans has put together for her. So if you click on this, you can go the whole flight and fly through like you're flying through the clouds, which is very nice for the students. And I should also point out that a big part of this is I keep coming back to this, to the field catalog, the field catalog, because that you can go through and you can actually simulate what you would be doing. You could go at a certain time, you can find out where the airplane is, overlay the satellite imagery, you can look at the camera, what's going out, and so students can go through this and systematically pretend like they're really on the flight and see what's going on. So it's a very nice feature. So I use this for my class, my last class last spring, and so there's also a part here which is the data analysis, and so she's got some Excel files which are kind of big, but you can handle them with some of the data, and also you can use the Arrow software if you want to make your own graphs from that, so you don't have to do that. So here's the flight that she had used on this one was it's 15 and 16, I believe, and here's just an example. This is one of our students in our class. I also have my TA who was in the classes back there. And so this was the RF14, RF15. And this, for example, is from one of the descents into the area at the beginning and one of the ascents out near the end. So you can think about this as being the 48-hour difference here. So here's the temperature, here's the dew point, and so the students can actually go in there and mine some of this data and look and see what's going on. So for me it was a very important tool, but you can sort of customize this to be whatever you want, and hopefully we'll add a couple more, maybe the 6 and 7, since that's such a nice one, we can add that to that. So I just wanted to point that out. And we'll try to figure out how to get the message out to a broader community on that, so I'm not sure exactly how we'll do that, but we'll figure it out. So let me just give you I'm going to give you a little summary here. And so basically the Lagrangian strategy with the G5 aircraft was demonstrated. Extensive cloud areas were resampled 48 hours later. I think we did a pretty good job of getting to the same areas. And so even though our initial reviewers on our proposal had some doubts about how this was all going to work, I think in the end it worked out, and it worked out pretty well. So I think it was great. So California and Hawaii on 7 missions. Unprecedented observations, the evolution of boundary layer structure in cloud and aerosol fields. And we think this is going to provide several cases, possibly for model evaluation and development. So that's the ultimate goal of this, is to try to improve our representation of these cloud features in models. We have extensive observations of key features of cloud system evolution were made. Mesoscale precipitating cloud complexes, gray cloud layers, ultra clean layers, boundary layer top. And I feel that we've really developed a showcase for aerosol cloud precipitation interactions, and we have that. There's also, I've got another slide here which is sort of the EOL highlights, at least from my perspective. And one is that I think we demonstrated the utility of the G5, particularly with the radar and LiDAR, for studying boundary layer clouds. People have said, well, the Hyper is really an upper aircraft, it's not designed for that. And we know some of the instruments did have their problems down in the boundary layer. The Chill Mirror, for example, some of the instruments overheated and other things. But overall, I think it really performed quite well. And I think the other lesson that comes from this is that by making some of your flights at the low levels and the rest at the higher levels, you could actually cover a pretty good range in making these measurements. So I think If there were some doubters as to how the G5 might work in the boundary layer, I think hopefully most of those doubts have been put away. The other thing I keep emphasizing, the field catalog, I always felt they should name it something different, because it's much more than a catalog in a way, because we use this for flight planning, flight operations, during the flight, teaching and learning experiences, and so I really want to point out that as a real highlight. I'm not trying to say other people's EOL contributions weren't good, but the field catalog was definitely a very strong part of that. So the last little part here I wanted to do is so I did some of this before, but I'll do this again because some retrospection, a little history. So this is where I sort of got involved in looking at these clouds, was back in 1976. And we had 5 flights with the NCAR Electra. And you notice the date here, 13 June 76. So it was almost one day after 40, is that right? That hardly comes out of my mouth, 40 years, is that right? Is that right? That's really bad. That's a long time. I don't think we learned very much in 40 years. It turned Anyway, aircraft sensors still get wet like they did when we were flying, right? Some of the same problems are still there. And, but we had this one particular flight here that was very memorable for my part. And so this was in 1976, and we had this area here, and there was ship tracks around, and actually, you got to remember at that time, we had to run up to the weather service to get the facsimile GOES output for this. This is a picture, this is a photograph of that. We didn't have the internet to get these pictures. So before the flight, we go out running up there, okay, let's go. And we saw this, so we got here. And this was we call this a broken cloud. I wrote about it in this 85 paper, and there's the same data set that Brost has used, so we've looked at that work. And the thing that caught my eye, though, and caught the pilot's eye and caught everybody's eye, was there was drizzle on the windshield flight. And kind of set us back a little bit. This project was led by Wayne Schubert and Doug Lilly. And Doug had put together his paper, was it 69? Do I have the right date? 68, I always get it wrong. 68, Doug Lilly put his paper. And Wayne, a number of years after that, started working with that paper and said, wow, we really need some measurements to look at that. Now, there was no cloud microphysics in that simple model. It was all turbulence, and the TKA budget was used to close the model. It was a simple mixed layer model. So there was no drizzle on the windshield in that model. And so this was our first realization that, there's something else going on in these clouds. And you can particularly, the ship tracks are sort of a giveaway that there's something going on there that has something to do with aerosols and other kinds of properties that were going on. So for this was a real eye-awakening experience, I guess, from my perspective, 40 years ago. And so I guess the question is, have we made progress? So here's Jonathan kindly provided this image of our nice. Now we didn't have rain on the windshield. There was rain on the windshield, but I wasn't up there. I did see it a couple of times. But pilots reported rain on the windshield. The cameras showed it very nicely. And so CSET, 7 July. So have we made progress? I say yes. We struck gold. That's we know right where the gold is too. It's right there. And so I think we've done very well on that. And I just wanted to take the last minute here, a big thanks, because when the project ended, I didn't really get a good chance to thank everybody for all their contributions. Lou was helping us get this thing organized, and certainly we had so much help from people developing the radar, putting the radar, the LiDAR working. In addition, the PIs that were on the grant, they helped write the proposal. They did most of the work, actually. Wrote the proposal, helped fly on the flights. We had students involved, and they all got a chance to really help put this together. So pilots, of course. We can't get anywhere without pilots, and all the technicians and everybody that was helping. I'm probably missing somebody in all this, but I just really want to put a big thanks out to give my 40th anniversary here was quite appropriate. So I appreciate it. Thank you.
Okay, thank you very much, Bruce. Do we have any questions? Have you covered every possible thing?
Yeah, I'm really curious. On the slide before, you talked about striking gold as being the advance in the last 40 years. Could you be a
What
little
really
more?
is the advance?
Could you be a little more specific? Because to me, this is a big question. Meteorology as a field isn't that old, or as far as observations and cloud
Right,
models and
yeah.
stuff. What are the big advances?
Well, I think from our perspective, and even when we did those flights in 1976, and Wayne Schubert, was thinking about this. He said, well, wouldn't it be great if we could, make measurements all the way to Hawaii and follow trajectories to there? And he had this little model put together where he did the downstream evolution and all those things. He said, yeah, that would be really neat. So I guess in my mind, the major advancements are, one, we got the capability of making these kinds of measurements in a Lagrangian sense. I don't think we had that. I don't think we have had that previously. And two, we've got the use of the LiDAR and the radar together. And of course, we've got holodeck coming too. So that's the other piece of gold that's coming. And so we have other things. So to me, those are the big advances that we've made here, is our capability to look at this as a system rather than going out and making measurements and going back home and saying, oh, we did it, because just like we did, we went back home and we looked at that, and then years later we figured out what kind of what we were doing. But I think in this sense, I think we have made progress. I don't know if anyone else has any ideas on that.
Yeah, I guess I might add to that, these particle trajectory models, have enough confidence in those to believe where they take an air parcel in 2 days. I don't think we would have this exact.
That's true. We didn't have that capability, forecasting capability either at that time. We wouldn't have had that, for sure. So.
A third comment on that is that I think that there is an enormous progress in our understanding of what these clouds do for climate, and that cloud aerosol interaction in those days was probably just viewed as is a marine cloud going to rain or not rain, but not with the large-scale view of what does it really mean for what's happening in the world and in a changing climate situation.
Right, yeah. I think, as I said, when we went out and made these measurements, we weren't even thinking about aerosols. We weren't thinking about any of that. And the thinking at that time, even when we did these measurements, we weren't really even thinking about climate per se. It was another, Dave Randall and Slingle and those people later showed, yeah, these kind of clouds are important in the climate simulation. So they're a realization. And so then, I think we have come a long ways in trying to untangle some of these aerosol cloud precipitation interactions. But every time we go out there, we see gray clouds and ultra clean layers, and we still got a ways to go. So I don't think all the problems are solved. So after 40 years, we're not done. So
it seems to me that one of the really big differences back in that same time period, I had a couple of my first LiDAR images. I went to a turbulence conference, and I showed them to Tenekas and Deerdorf and Lilly, anybody who would look at them. And they just blew me off. The whole world at that time were mixed layer models, third order closure.
Right.
So the view of these things was totally different. It didn't have these cellular convection in it.
No, mesoscale. That's the other thing. I
That was
the
all
mesoscale
gone.
organization. There's a lot there. So maybe the right word wasn't to strike gold, but I think we made some progress.
Well, why not? This is the conclusion section of the paper.
Right. Well, okay. Well, we can say we struck gold then. We can work on the words for that. Rob,
Any more questions or comments?
I actually have a question. So, I think this was also, well, no, it's a first of a comment. I was thinking about this, and the part where we go from the maximum of the stratocumulus, which is about maybe halfway to Hawaii, I don't think there has been any measurements of that.
No,
barely any measurements.
That's true.
Anyway.
We'd always been coastal
And towards the maximum.
Right.
The same was true in vocals. The same was true in
Right.
many
All
campaigns.
these parts, we never really got to this transition area. So this is our first measurements, and maybe this is why we hadn't seen the gray clouds so much before, because we never had been there before.
I guess HARP was an example, maybe, but that
That was from over the island, by the island, right?
more,
It was
more island
coastal, and
influenced. Yeah.
They were orographically forced, some of those clouds, weren't they? Yeah, so that was a little different. But that is true. We really haven't had that. We've had some of the stuff in the Atlantic with RICO and some of those things. But that's a good point. You know.
Yeah, RICO was kind of sort of the more developed trade wind. This was sort of this transition, this breaking
is sort of the
up of the
transition
cumulus.
kind of area that there were some with the Magic cruises, but you know that's a little different picture. Yeah, from the ground. They had a ship that went back and forth, a cargo ship with a instrumentation on it making measurements. But they didn't have that advantage that we had, was we could actually try to sample the same air mass 48 hours later. They had to take what they got. You know, that was there. So, okay.
I have one question, if you don't mind.
Yeah.
Looking at this ancient history picture, we see the ship tracks very clearly. I don't remember seeing ship tracks in the satellite pictures from this project.
There were some farther to the north on some of the days that we had. We didn't find any in this, like in this picture here. We didn't find a lot in this area here. They were more up in this area at various times, and that's a good question. Why not?
I was wondering if it was a difference in the ship's propulsion or...
No, I think it was a difference in the conditions. These are some, I mean, Rob might call this a collapsed boundary layer, but if you look at the thermodynamic structure, I'm not sure it was a collapsed boundary layer, you know, because there was still quite a bit of water there and there was a lot of things going on. But clearly it was very clean though. We had really low CCN concentration. So you need the very clean environment in which they can form. And maybe we weren't that clean. I don't know. I mean, that is a good question though to look at. So.
Thank you. Any more questions or comments? Yep.
The path you showed make me feel like it's kind of like atmospheric rivers, right? The path, the trajectory you showed.
So like a what?
Like the aircraft trajectory, the path you took make me feel like it's atmospheric rivers you go through.
Atmospheric rivers?
Yes.
It's kind of the opposite. This is where you're having a flow ahead of a cold front that takes a lot of tropical air up towards California.
Oh, okay.
So you can on the difference. Oh, sorry.
Oh yeah.
Yeah.
Oh, it's like.
Well, I got the microphone here, but I hadn't thought of it that way, I guess. I have to think about that, yeah. This is coming towards the coast, is what you're saying.
Yes. Yeah, you are like going upward, right?
Right.
Yeah. And what I'm thinking is like if the atmospheric rivers, they have different paths, right? If it's like different angles toward California, whether you will see different like cloud evolution or something like that.
Right. Well, yeah, I think that makes a difference, particularly in the coastal areas, it's probably more prevalent.
Oh, okay.
We were always struck by this image here that if you look, this looks like Point Sur, or is that Point Sur?
Oh, you mean to?
It almost looks like that, and you know, it looks like someone took a cookie cutter and just moved the clouds out, you know, from it there. So, but yeah, this area in here is also, you know, very complicated because sometimes the flow comes off this, and so it just depends on really the position of the high and what's going on there. But some of that may affect what's going on downstream, but.
Okay, yeah. Another question is just to satisfy my curiosity. So I saw like the cloud is toward the east, and you when you take your camera, like the real-time series showed like it's the cloud actually moving toward east, or it's the water vapor like cloud formed and disappeared and the water.
You were looking at the satellite imagery?
Yeah, something like that.
That box on the satellite imagery, it was kind of showing, it was consistent with the flow and the low levels, if that's what you're referring to.
No.
Or you mean from the airplane?
No, because I do modeling and I calculate water budget. So I just wonder, like, if the cloud actually moved toward the east, or it's the water vapor in the atmosphere.
Well, one would like to think that it's probably not the same clouds that are there. That these clouds evolve in time.
Okay.
And so it's not necessarily, you know, you can't think about this as all being just a big cloud mass that's moving along this way. It's very dynamic, and lots of things are going on inside inside the boundary layer. So from that perspective, I think you can only think of it as some air masses is being advected along, and somehow the clouds are responding to the large-scale subsidence or the differences in the surface fluxes or the aerosols or some other processes that are going on there. So.
Okay. Yes. Thank you.
Okay.
Any more? If not, let's thank you, Bruce. And as you said, the CSET meeting continues for this afternoon and tomorrow.
Right, okay.